Okay, so now we come back to the real show, the real fun. And as I think you remember that we have a list of variables, and the data view is that you can see the data, and the variable view is that you can see the variable. Now, you have to be, before you start performing analysis, I give you some suggestions. My first suggestion is that if the variable is in decimals, okay, please increase the decimal size. Because if you see the original variable here, this variable is 0.000290, yeah? It's very small variable. But if you don't change the variables, they would look 0.000000 or some very, very small. So they would lose their significance. So what I recommend you, that for every variable, you should have 4 or 5 decimal places. It doesn't make any difference. Okay? So what I do here, I change the decimal spaces. So of course I can increase 3, 4, 5. I think 5 is enough for everything. 5 is enough, yeah. So I can manually change the decimal places. Oops. 3, no. 3, 4, 5. 5 is okay. We can round off at the end, no problem. 2, 3. 1. And now when you have the data view, it looks better now, yeah? Now all these decimals are recognized because now the width is increased. Okay, now we go to analyze. I hope you remember. And if I do the, have we done correlation before? Correlation, you remember? We're done. Okay, let's go to regression. Go to regression, yeah? And in the regression, the most often regression that we use is called linear regression. You can see here, the values are linear, yeah? There's no square, there's no cube in the variables. So we take the variable as such. So we take the linear. So you remember the commands? You can write down the commands if you want. Well, they are recorded anyway. Analyze, regression, linear regression. Right? And then, if you remember, we took, let me do again. Our G variable was dependent, yeah? So if you see there's a dependent variable, yeah? So what I do, I select the G variable as dependent. And let me first reject them and then accept them again. So, and once I have the other variables, I can select them all, or you can choose, pick and choose which you want, which you don't want, and you can move them in independent variables. Method could be enter stepwise. To be honest, it doesn't matter much. Enter method is the easiest way, enter. And then we do nothing else on this page. There are some more options, but we don't really care. Okay, what we care is we go to statistics here. And in statistics, we choose the confidence interval. Can you see the confidence interval? 95%. So if the confidence interval is 95%, what is the level of significance? 5%. It means that by default, the system, the SPSS accept the results which you can say with 95% confidence. But I recommend you that it's not a bad idea to make it 90 so that we can accept 10%. In statistics, in econometrics, in empirical research, up to 10% level of significance, things are accepted. Right? It means that your minimum level of confidence should be 90%. And then I take Durbin-Watson test. I tell you what it means. Then we don't R square, descriptive. Well, descriptive we have done already, but it's not a bad idea to take it again. And then we select the collinearity diagnostic. These are sounding very rocket science type of words, but I will explain them to you. But have you seen it? That we went to statistics and we chose estimates for sure. Without estimates, it makes no sense. Confidence interval is 90%. Yeah. Then we have the Durbin-Watson test. Then we have the R square, no changes. That's fine. Collinearity diagnostic. So can you see it? So then we click OK. Then we have the plots. Your dependent variable is what? Who's your dependent variable in this model? G. The values that we enter in SPSS space are the actual values. Yeah. They're the actual data collected and then we enter in SPSS. But are you interested in finding the estimated values of dependent variable? For example, if I say that intelligence depends upon parents' education, just simple variable. Then we have the level of intelligence and parents' education actual, both are actual. We enter these data in SPSS, we run the regression. Do you want to see that what is the estimated value of intelligence? And the difference between them is error. You know what is meant by estimated values? Theoretical value, hypothetical value. What should be the theory's value? According to the theory, what should be the value? If I give you an example. You throw the how to say it? You throw the toss coin 2 times, 10 times. It could be possible that you have 7 times head and 3 times tail. This is the actual finding, yeah? But what should be the theoretical finding of head and tail? 50-50. So the theoretical value is 5 head, 5 tail, and the actual value is 7 heads, 3 tails. There's no guarantee that when you throw the toss 10 times, it will be 5 heads, 5 tails. There is no rule of it. But in theory, we expect that there would be 5 heads, 5 tails, because they both, head and tail, have equal chance of showing up. So this is the theoretical value, but the actual value could be different. But let me take it. See here, there is a, can you see Z predict, Z predict? It means what? Adjusted predicted value. What would be the predicted value of the numbers? And then we have normal distribution plot. And then nothing else we need, to be honest. We have everything now. And then we click continue. Is anything in save? Yes. Actually, you know what? I made a mistake. Oops, sorry. We cancel it. We'd have a plot. This we don't need. Continue. Yeah. This value, save. The unstandardized. This is the predicted. This is the expected value. Sorry, it was my fault. The theoretical value, the example I gave you, that you have 10 tosses. There are 7 heads, 3 tails, but in theory, it should be 5 heads and 5 tails. This theoretical value is this here. Okay. I'm sorry, I said other way around. We need something else. To be honest, we need nothing else now. Okay. And we continue. And then we click OK. This is our SPSS output. Should I do it again? Once again, all the steps, because I know that it's not understandable in the first attempt, to be honest. So no problem. Let's do it again. Analyze regression, linear regression, and then you can reject all of them first. So we make it empty. Yeah. So our G variable is dependent. We agreed. Yeah. So this you highlight and you take it to the activity area. And then all of the variables are your dependent variable. Yeah. So I call them dependent variable. Sorry, independent variables. Yeah. Okay. Are you fine? Yeah. Now we need some enter is a good method, is a decent method. I think enter should be fine. Now there are some additional add-on functions, and I will be using this, this, and this, not more than this. First, I use statistic function, statistic plot and save. Statistics. You want to see the estimates. Estimates are these betas, you know, the beta 1, beta 2, confidence interval, by default, it's 95%, but you can customize it, but don't take less than 90. So we don't accept it. Durbin-Watson test, you take it. I'll tell you the reason why. Once the output comes, I would give you the reason. And then model fit or descriptive collinearity. These are the three things which you must take. Okay. If you want to take a pause, you can write down that what you should take. You should take estimates. You should take confidence intervals. Covariance matrix, I don't see any reason of taking it. Durbin-Watson, you should take. Model fit, you should take. Descriptive, you know descriptives? Mean, median, mode, range, maximum, minimum, standard deviation. Remember we had the first lecture? These are those. So they will come again by default. And then collinearity, diagnostic, you should take. I'll explain it once it comes. Continue. Then comes plots. In plots, nothing else you need. You don't have to take anything except for the normal probability plot. This will show how your data look like. Because you may have, look, in this case, we have 111 observations, right? Do you want to see how they observe, how these observations look like when you plot them on a graph? So this you should take, continue, and then in save, you should take the unstandardized, look at the value, predicted values. You know the example of tossing the coins 10 times. So are you interested in getting the theoretical value or not? I don't think you need anything else here. And then again, continue. And then click OK. There we go. We press the nuclear button. It's getting. Yeah. Yeah, it's fine. So now we get the mean, the standard deviation, and the number of terms. This is quite simple to explain, okay? I will not go for it. But the real thing is this. And here you can see the correlation. All right? You can see that there is a correlation. And if you see the diagonal matrix is always equal to 1. The diagonal, why so? Because here you are correlating B with B, C with C, D with D. That's why, because it's in the row and the column. Why? So obviously, the correlation of a variable with itself will be 1. And I hope you remember that the maximum correlation is +1 and the minimum is -1. But the point is not this. The point is not the size of the correlation. The point is the sign of the correlation and if this correlation is significant or not. All right. We here little bit deviate from statistics books. Statistics books say that if the correlation is more, 0.9, 0.93, that is a correlation. But here what we say that size of the correlation may matter, but what matters is sign. Is it plus or minus? And moreover, is this correlation significant or not? Now here you see the level of significance. For example, look at this correlation between H and E. The level of significance is 0.65. Okay, it means that you can say with 93.5% confidence that the correlation between H and E is significant, and it's not just because of some random fluctuations. You get my point? You can say with 93.5% confidence, because here the level of significance is 0.65, which means 6.5%. That you can say with 93.5% confidence that the correlation between H and E is significant, even though the correlation between H and E is just 0.145. Very small. Makes sense? If I look at statistics books, they would say, oh, this correlation is not much. But what matter is that, are they significant or not? Yes, they are significant. On the contrary, you can see some correlations which, let's say E and D. How much is E and D? E, no, it's not less. I want to see some big correlation, for example. Look at this one, yeah, C and B. C and B. Yeah, this is very significant. Look at that. C and B correlation is negative. So the relationship between C and B is negative, and it's 0, 0, 0. It means what? You are saying almost with 100% confidence that the correlation between B and C is significant. Does it make sense or not? Are you able to make interpretation or not? You are saying with nearly 100% confidence. It's nearly true, absolutely true. On the contrary, look at this correlation, F and C. The significance level is 0.225. And if I see the actual correlation, it's 0.73. It's not much, but you know what? That's not more important. The important thing is this, 22.5% significance. It means your level of confidence is just 75, 6, 7, 8%. No, no, no. Unacceptable. Unacceptable. The message I'm trying to give you is that the size of the correlation comes secondary now. What matters is, and here we deviate, here the empirical research or econometrics would differ from the basic statistics books. Statistics books say that if the correlation is close to +1 or -1, it's very high correlation. Well, it can be here also, but is it significant? And if it is not significant, then what is this? It is just some random fluctuation. It's a fluke. You know the fluke? You hit the dot and you're not expert and then it hits. No, it just hit randomly, by chance. So it's just by chance that something exists, but that's not truly a reliable finding. It can be a random outcome. It can be a random fluctuation, but the variables don't have any real sensible relationship. You don't have enough evidence to prove it. And what is the evidence? Max 10% level of leeway is given. It means maximum level of benefit of doubt is 10%. It means the minimum level of confidence is 90%. Max benefit of doubt 10 means minimum level of confidence, which is accepted, is 90%. If it is below 90%, never accepted. The relationship may exist, but you don't have enough evidence to prove it. Like the inspector brought the data that I think this guy is a murderer, but the chief cop says that, do you have enough confidence to say? Okay, then leave him. The person is innocent until proved guilty. Okay? If you're, well, I think I'll explain it here. And then we go to the coefficients. Look. Alpha is the constant term here. Look, the constant term we wrote here in the model. Maybe you can see it. You can try to show it. And then the first term. So that A variable, A variable beta 1 is this. B variable, beta 2 is this. C variable, and beta 3 is this. Yeah, make sense? Constant is very important. Imagine your relationship that you want to study is that sales depends on advertisement. That's your research, the model. And you find that sales is equal to alpha plus, sales is equal to 0.3 plus 0.7 advertisement. It means what? If I measure advertisement and sales in 1,000 euros, what I'm trying to say here is that if you spend 1,000 euros on advertisement, your sales will increase by, what is 0.7 of 1,000? 700. Does it make sense? So if your beta 1, let's say, is 0.7, it means that, and you are measuring, it's very important that how you measure the variables. If you're measuring them in thousands, so you're trying to say that by spending 1,000 euros on extra euros on advertisement, you can expect 700 euros increase in sales. And why did you use the word increase? Because the sign is positive. Imagine the sign is negative, then you can say opposite, that by spending 1,000 euros extra, you can expect 700 euros decline in the sales, right? Well, it can happen, as we discussed, that the advertisement campaign can backfire. But what is the meaning of this thing? 0.3, constant term. It means that there would be still some sales, even if there's no advertisement. Even if a company does an advertisement, can it still expect some sales? It can be very less, or it can be even negative. It doesn't have to be positive. It can be negative also. Right? So this is a constant term. Basically, it has not much role to play in the analysis, but it's only a matter of interpretation. Sometimes it matters, sometimes it doesn't matter. But to be honest, if I have to use conclusive words, in nutshell, we don't really care of it. It doesn't really make any sense. Okay? So it is there only because it shows up. Sometimes it matters, sometimes it doesn't matter. Okay. And then comes, we always see the unstandardized coefficients of beta. This beta, this is also beta. This is standardized, we don't say it, but we always see the unstandardized coefficient of beta. Yeah? Yes or no? And then we see the level of significance. Of course, for the constant, we don't care anything. We don't care. Look at this variable, second variable, B. The level of significance is 10.9, yeah? What is the maximum acceptable? Huh? 10%? It's a very unfortunate case because it's 11%. 10.9 means 11%. Yeah? So the impact of A on G, remember G is your dependent variable, yeah? The impact of A on G is negative. However, we are almost losing the significance. So we don't have, well, now I shouldn't say anything. You can still accept it because 10 and 11 is a bottom line case. Yeah. But if I go by the book, I would say that B have a negative impact. I would say B, I need to go back. I would say that, sorry, this is A variable, not B, I'm sorry. So I would say that variable A affects G negatively. However, the finding is insignificant. There exists some random relationship, but it's not a very, I don't have enough confidence to say that this relationship is really reliable. And then comes this is absolutely out of question. Can you see? This is absolutely out of question. So before I make any comment on the size, look at that. The size of the coefficient is so big, 17. I think it's the largest, or maybe one of the largest. Yeah, but look at that. This size doesn't matter here. What matters is, the first thing which matters is the level of significance. Here, the level of significance is unacceptable. So on, so forth, that we are on F. F, G, F, H, and I. F, H, and I. These are the three variables which are the diamonds, gems, because you are saying almost with 100% or at least 99.99% confidence that these variables have an impact on your dependent variable known as G. Make sense? And one more thing. Lower the significance means larger the confidence, larger would be the T values. T statistics come automatically. Okay. Basically, it comes by dividing. Can you see here the T statistic? Yeah. So you are dividing the standard error. But the point I'm trying to make is that if your significance level is low, your T statistics will automatically increase. Larger, those variables which are acceptable, they have high T statistic. So in this case, you have the hypothesis, yeah, beta. So your null hypothesis was beta 1, beta 2, beta 3, all are zeros. So this part is very important. And you are able to prove now that your beta, was it this one? F, H, and I. So F, H, and I means your beta 6, beta 7, and beta 8 are non-zero. Sorry, I can say that beta 1, beta 2, beta 3, beta 4, and all else are zero, even though they are not zero. But I don't have enough confidence to say that they are not free, they are not away from zero, they're nearly zero. And they fall in this rejection or acceptance zone. Can you see that? There is a difference. Beta 1, beta 2, beta 3, they are different from zero, but they are still in that zone where we accept null hypothesis. And when you accept null hypothesis, you reject your alternative hypothesis. So basically, you are trying to say in simple words is that beta 1, beta 2, beta 3, beta 4, beta 5, they have no impact G variable. They're impact less. There may be impact, but there may be theoretical impact because that's why you build your hypothesis. But you don't have enough evidence to prove them. After all, don't forget that these variables came from the literature review. But in your case, you don't have enough confidence to accept them. However, beta 6, where are they? Beta 6, which is F, beta 7, which is from H, and beta 8, which is from I. You have enough confidence to accept that they make impact, they not only affect G variable, but you have enough confidence to say it because the level of significance is very, very low. Does it make sense? Yeah? Okay. We don't see this, we don't see this. The next thing which we see is the collinearity. Remember I told you that there is collinearity thingy. Remember once we were choosing, I was asking you to take the collinearity. The collinearity is very important. The collinearity is shown by two variables. The first is called collinearity tolerance, and the second is called statistical variance inflation factor, VIF. Variance inflation factor. And the other one, the first one is called collinearity tolerance and variance inflation factor. Collinearity is very important. Have you studied collinearity? No, wait a second. Very important. We want to see, ideally, we want to see more and significant relationship between A with Y, A and G, B and G, C and G, D and G, E and G, F and G, H and G, and I and G. That's why we chose them, because we think that these have strong impact on our dependent variable. The problem is that let's say A and B. Example, A have less impact on G, B has less impact on G, but A and B are highly correlated with each other. This is a problem. And this problem is called collinearity, that we want to see more of the relationship between the independent and the dependent variable. But the problem is here that the independents are more related or more correlated to each other. This is a problem. This is a problem. And the simple statistics mantra is that if your collinearity tolerance, if you see that this is just 1 over this, so 1 divided by this is this, 1 divided by this is this, 1 divided by this is this, and 1. So basically, this is just reciprocal. Can you see it? The simple mantra is that if this variable, if this column is less than 0.10 or 0.1, if it is less than 0.1, it means 1 divided by 0.1 will be equal to 10. Yeah. If this is below 0.1, or let's say this is more than 10, because 1 divided by 0.1 is 10. If this column now values are below 0.1 and this column values are automatically more than 10, we have a problem. We have a problem. Fortunately, none of them is below 1. So this value we always want to see more than 0.1. In other words, when you divide this 1 by this, you get this. When you divide 1 by this, you get this, okay? So fortunately, none of them is a problem. But the thing is that what if there's a problem? What if there's a problem? It means that if, let's say this value is 0.02, this value, we have a problem. Then there is something wrong with f variable. We need to see that which variable f is highly correlated. Then we go back to the correlation matrix. And then we see which variable f is highly correlated. And then we find that f is highly correlated with h and b. Then we don't take f with h and f with b in the same model. So we have more models then. Do you get my point? Let's say f is highly correlated with h, let's say. It means that then you have to run this model 2 times. One's with f and one's with h. F and h should not remain same in the same. Do you get my point? Because what we see here is that for f, let's say this is 0.02. 0.02 is dangerous because this 0.02 means it's 50. And I said that if it is below 0.1 and if it is above 10, it's dangerous. And if it's 0.02 f, it's dangerous. Then what we see? F correlation. So we see the F column and who F is highly correlated. And we find that F is highly correlated with H. Then we have to run this model not once, but 2 times. Once with F and without H, and second time without F and with H. They will not stay together because they are highly correlated with one another. So keep them separate. Separate means you run the regression 2 times. You get my point? Otherwise, it could be a problem, but this doesn't happen very often. It happens only in the extreme cases. And as you can see here, that luckily, in our model, the collinearity tolerance is much, much more than 0.1. Okay, so there's no danger. This we don't really care. Look, our data. These are the theoretical values, the standard line, yeah, the black line, and this blue dots are our actual data. Actual data of what? Dependent variable. Yeah, so this is the theoretical data, the black line, and the blue snake is the actual data. What do you observe when you see this kind of relationship? Are they quite close to one another, or are they like this? Are they like this kind of thing? Or fluctuating like this? Huh? Very close. So this is also a good sign that your real data is not very far away from the theoretical or the expected or estimated values. Make sense? And then one more thing which you need to see. You see, it's like a, how to say it, when you go for the blood test here, they take one drop of blood, and then there's a main problem that why you get the blood test, okay? But when you get your blood report, you have all type of maybe 5-6 pages. Some of that information matter, some of them doesn't matter. So you can see a lot of things which matter, but there are also lots of things which don't matter much. So we only see what it matters. The first thing we see always is the correlation matrix. And then we see the correlation is significant or not. Then we see the estimates, the coefficients. We always see the unstandardized coefficients. That would show the positive, negative relation, or the size of the variable. But more than the size, the most important thing is significance. It means that we had around 10 variables. How many? 9 independent variables. So we thought in the theory that there are 9 variables which have an impact on the dependent variable, but we have only evidence to prove the impact of 3 variables. So 6 variables, there might be theoretical relationship. Unfortunately, we don't have enough evidence to prove them right. And if we can't prove them right, then we accept the null hypothesis. But where we have the enough evidence, in case of B, 6, 7, 8, then we reject the null hypothesis and we accept the alternative hypothesis. Okay? And then the next thing we see is that ideally, we want the effect of individual independence more on the dependent variable. But sometimes it happens that, let's say A and B, they have less individual impact on Y, but they are highly correlated with each other. That could be a problem. You know what it means? If A and B's correlation is 0.93, 94, 95, what it means that why I'm taking A when I could take B, or why I'm taking B when I could take A, because they're so much correlated. They are like one. For example, if I want to study the impact of education on crime rate, and I'm taking education which you get in 4th standard and in the 5th standard. Come on, 4th and 5th standard. The same student who study 4th standard go to the 5th standard. So the correlation between 4th and 5th standard could be highly correlated. So you could take only one class. So if you take 4th and 5th standard both, they seem to be highly correlated. Take either 4th or 5th, but then take somebody from the secondary school, secondary level, after some gap. Because basically the students in the 4th and 5th standard, they have the same age group. So what difference of 1 year make on the crime rate? Not much. So then our result can be spurious. Spurious means poisonous, a little bit, not so good, not very pure result we can get. So in that case, and this we know from this column, collinearity, tolerance. Look at the word tolerance, and the minimum it should be 0.1, okay, which means the maximum this would be 10. So this can't be more than 10, and this cannot be less than 0.1. Fortunately, we are safe here, all right? But if it happens, then go to the collinearity correlation matrix and find which variable is troubling, and then see which other variable B is highly correlated. And if B is highly correlated with H, then in that model, don't take B and H together. Either take B or take H. So in the one model, you take B, don't take H, do everything again, but this time not with B, but with H. So you can separate them. All right. So it could be possible that the same regression model is run 2, 3, 4 times. And if there's lots of collinearity, which means that when you see this variable, most of them are below 0.1, then definitely there is something wrong. you have taken wrong variable, or you have taken right variable but measured wrongly. Something wrong you have done, then you must speak to your thesis supervisor that, Shab, we have messed up. Then there is something wrong. So talk to your supervisor and ask that there's a problem. But as I said, it doesn't happen very often. If it happens very often, then something is definitely wrong with your data collection. Yeah. One more thing which I want to share with you is this. ANOVA. Have you heard ANOVA? Analysis of variance. Analysis of variance also comes automatically in the system. Analysis of variance is that if you have the Y value, what is Y value? The G value. So if you have the, how to say it? Let me plot it. Your dependent variable is G, yeah? So this is G, that column, and we have 110 G values because our N is 110, no, 109. Yeah, N is 109. You know how to find the mean of G? You just add all the values of G and divide by 109. Let's say this number is 13. And this is G1, G2, G3, and so on. You find out G minus X bar G, which means G1 minus 13, G2 minus 13, G3 minus 13, and so on. And then square them. Square them. And after you square them, you add them. Add means sigma. So from each value of dependent variable, which is G, you minus its average. And then square it. If you don't square it, it'll be 0 for sure. Right? So you have to square it. And then after squaring, you add them up. This is this. This shows the total variation. This shows the total variation in your dependent variable. This, when you add them up, it shows total variation in the dependent variable. But that's not the point. The point I want to prove is that how much variation in the dependent variable is explained by the independent variables. You know, that's our purpose. Why we take so many independent variables in this model? Because we want to test them. How much change in A, B, C, D, E, how much change in G is explained by change in A, change in B, change in C, D, E, F, H, I, and so on. So question is, how much change is explained by the regression coefficient? And here we go. Okay, does it make sense? Yes or no? Can you see it? And when you divide this by this, you get 0.374. When you divide, this is the total variation. This is the variation explained by these different independent variable. And when you divide the variation explained by the independent variable and the total variables, we get R square. It means that 37.4% variation in G is explained by variations in A, B, C, D, E, and other variables. It means that there is still around 62.6 or 63% variation, which is not explained by. So the 63% movement in G is unexplained by these variables. It may lie somewhere else. You know, we don't want to be the angels that we want to explain all the movement in G by the taken variable. It could be possible. We took the variables by a lot of studies, a lot of literature, and we found that these variables we have some hypothesis. Unfortunately, 37.4% variation in G is explained by A, B, C, D, and others. So there is 63% variation, which is somewhere else. We don't know. But empirical evidence based, I would say that 37.4% R square is not a bad R square. You know, it's not a bad R square. It's pretty good. Okay. And then we have the adjusted R square. Adjusted R square is a more qualitative thing. You can increase the R square by adding more and more variables. The question is, are those variables even relevant? For example, the level of intelligence of child is a function of parents' education, level of education, quality of education, your upbringing, your family background, and all that thing. And then two variables are the amount of socks sold in the city and number of pizza delivery boys in the city. You find something awkward? The level of intelligence depends upon age of parents, education of parents, level of education the child has, the quality of education, the family surrounding, the social benefits, and blah, blah, blah. And then one variable is the number of socks sold in the city and number of pizza delivery boys. No connection. But if you take them, your R square will be more. R square will still go up. Wait a sec. These are nonsensical variables. To filter out the useless variables out. Otherwise, I can add 100 more variables and I can be nearly, my R square can go up, 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 up. Is it even sensible? No. The sensibility of variable is taken by adjusted R square, which means that it filters out nonsensical variables. All right. So that is why in many cases, in my research, I prefer to write adjusted R square rather than R square. Okay. So you can see the difference that here R square is 37.4%, but the adjusted R square is 31.7. Normally this is lower than this because this might have some useless variable. And this takes away the impact of useless variable. SPSS is very smart. It takes away the less relevant variable. So something is less relevant, which is taken away by not the variable is irrelevant, but the movement variation is unnecessary or meaningless. So that is taken away. So I would rather look at this. I would rather look at this. Yeah. Make sense? So quick recap. You have the data in Excel. You transfer this data to SPSS. Okay. Data view, and the variable view. I strongly recommend that you must increase decimals if you have some data in decimals. I had at least 3 columns in decimal, which without, by default, it shows 2 decimal points. But if you show 2 decimal points and everything is 0.02345, 0.021, then all will be 0.2, 0.2, 0.2. It makes no sense. So increase the decimal points and also have some name. Have some names also. Okay. And then the next thing you do is that you go to analyze, regression, linear regression. Okay. Then you pick up who is your dependent and who is independent and move them to activity area. This is the dugout, and this is the activity area. And then you choose statistics, estimates, confidence interval 90%. By default, it's 95, but make it 90. Dublin-Watson test, you choose and then click continue. Sorry, something else is there. Yes, there is a more model fit, descriptive, and collinearity diagnostic. This is what I was talking about, IV and tolerance, collinearity. So this is what you need to pick up, yeah? This is okay, and then plots. Just normal distribution, because you should see how your data look like on a graph. Does it look clumsy or does it look systematic? And then you see the save, and here you want to see the unstandardized value. You want to see the estimated value of the dependent variable. That's it. And by the way, I can show you here something, that when I have the output data, I have only A, B, C, D, E, F, G, H, I, J, but I have pre1, pre2. Do you know what it is? Because the same variable, but came twice actually, because I gave the command 2 times, yeah? This is the estimated value of G. Didn't I say that this is the real value of G? But you also want to see the estimated value of G, theoretical value of G. This is the theoretical value of G, right? And how did it come from? Why did it come from? Because when we analyzed it, and when we went to regression, look carefully, I went to save, and I picked up unstandardized predicted values. This is why this theoretical value has come. And the difference between the actual and the expected value would show how far our expectation from the reality. This is quite, in many researchers, you want to see this kind of, let's say you want to interview somebody, survey, yeah? You want to send some surveys. You think, hey, this should be the normal reply. You know, on a scale of 0 to 5, 3 should be the normal reply. That's your theoretical value. And the real value is 1, 2, 4, all that. But you want to see that how far the deviation between the reality and the actuality is. And then you want to see the value. The real value for sure is this. The real value for sure is this. But this is the theoretical value of G. And what else I need to show you? That you have the constant, which we don't care. We have the independent variables. The first thing we see is that are independent significant or not. We had 9 independent variables. 3 are significant, 6 are. We don't have enough confidence to prove them right. And if we don't have, then we reject the alternative hypothesis, hence we accept the null hypothesis. But for those where we have evidence, we accept the alternative hypothesis and we reject the null hypothesis. And then we want to see that how much correlated the variables, the independent, are between one and another. And if these values are 0.10, if this column is less than 0.10, or this column is more than 10, we have something to be worried of. Okay? And then we can't take those variables together. And then the question is, what is the total variation in your dependent variable? Well, the total variation is this. Question is, how much is explained by A, B, C, D, and others? Well, this is this. And when you find this ratio, this divided by this, it comes R square. It means that 37.4% variation is explained by all these independent variables. 63% lies somewhere else. We don't worry about. We don't have to change the world in one research. We can never do. We shouldn't even think about it. But then there's small catch is that this R square's value can go up even if you add some nonsensical variables. Then we use adjusted R square. Adjusted R square is a decent value. It's a nice value to see. Okay. All right. Now something else is left. A few more things are left in this output, which we shall discuss when we meet next time on 3rd. So when we meet on 3rd, I will spend 15-20 minutes. I will steal away and then I will explain some more things, but I don't want to stuff your minds with lots of things today. But please go through it, see the recordings, and if you get stuck, see it again and ask me if there's still problem exist. And then we meet on 3rd of May in the computer lab, and 2-hour session, but I would take at least 15-20 minutes and redo a few things and discuss a few things which I haven't discussed today with you. And then I will give you open space, and then you do by yourself. You can bring your own data from somewhere if you wish to, and because otherwise, if you experiment on the same data, the same results will come. All right. So yeah. So maybe you can download the data from somewhere else, some other source. Or you can change the variable. Next time you can make some other variable dependent and the others as independent. That's what you can do. See how this goes. Okay. So thank you so much, and for your tolerance, for your endurance and your patience. Good luck, and we will meet on 3rd of May. Thanks a lot.